Hello, this is Calculus 1, Lecture 8b, Inverse Functions. My name is Scott Grizzard from the University of South Florida. Today what we're talking about is inverse functions. Last time we talked about linearization and differentiables. Today we're going to be talking about inverse functions, one-to-one and onto, what that means, and the derivatives of inverses. And I mentioned last time that differentials was one way you could get at the derivatives of inverses. There's another way you can get at them also. So this is sections 3.1 and 3.2 in the book. Now, normally this material is supposed to be in Module 2, but we don't usually ask test questions on it. So I kind of wait till the very end at 8b. You still need this stuff in order to do inverse trig in Module 3. So what we're going to do is we're just the last lecture before the test. We're just going to do the bridge material before Module 3. So turn back the Wayback Machine. And remember what we had? We had this definition of a function where we had two sets. We had x and y, and we had this kind of conception of f taking things from x to y so that every x gets used and no x gets used more than once. So so we have some x space, some y space, and we're just going to let the x space be ABC and y space be 1, 2, 3. And so I had this idea, I had a function f, which was A1, B0, C2. So every x was used and no x was used more than once. Now, instead of just thinking about the function from f, now what I want to think about is I want to think about a function g that takes values from the y space and returns them to the x space. So what I want is my g, if this is my f, I want my g to take all of those values just back to where they started. So the g is going to be 1a, 0b, 2c. So here's the g in green, and a goes to 1 through f, and then g takes it back to a. And this is what's known as an inverse, okay? First of all, g forms a function, right? So every input is used, and no input is used more than once. Now, those inputs here happen to be y's. But remember, this is a function going from y to x. So in other words, the x space of g is the y space or something like that, right? You don't want to say that, it's confusing. But the input space is the y's and the output space is the x's. Okay? So this is what we refer to as an inverse. Okay? Now, notice something here. If I compose these two functions, right, I get back to this function x, right? So when I compose gf of x, what I end up with is this function x, right? So I've got g, right? If I do f first and then g, the composition equals x. And this function right here, we call it the identity function, okay? So let's add a little bit of space here. So we call this function the identity, all right, on x. So okay, so we have this function. If x is just some set, we have the function f of x equals x. This is the one that sends x back to itself, and this is called the identity function of x, okay? And it's generally just labeled IDX. So the x space for this is x, and the y space is also x, and it just maps itself back to itself. Now, and that's what the arrow diagram would look like, right? It's just, it just maps itself to itself. And if we look at the graph of this function, f of x equals x, we can see here it's just the diagonal line, right? This 45-degree line right here. And like f of 0.5 is 0.5, f of 1 is 1, and so on and so forth. And that's going to be a little important to us. So what we want to do is we want to define an inverse in a very technical sense here. And this is how we do it. It has this property where if I could compose the two functions, I've sent myself back to myself. But it also works in the other direction as well. Notice that f of g of y, if I take 1, if I start with g, if I start from the y's, and then go to f. So if I map here 1, if I start here, I can go to a and then back again. So it not only works for the x space to send everything back, it also works for the y space to send everything back. So if I start in the y space, I wind up back at the same number in the y space. So we're going to say let x and y be sets, f a function from x to y, g a function from y to x. So f is going this way and g is going that way. Okay. G is the inverse of f. If for every x in x, g of f of x equals x, and every y in y, f of g of y equals y. So in other words, if I compose g and f together, I wind up with the identity function of x. And if I go in the other direction, I wind up with the identity function for y. Okay, so let's do another example. Let's consider f, from the reals to the reals, f of x equals x cubed. Okay, so my x spaces are and my y spaces are, and I'm cubing things. So what I'm going to wind up with for an arrow diagram, and generally arrow diagrams are best when you do inverses, although, the graph of the regular function can help. Right? If I'm at 0 and I cube it, I go down here to 0. If I'm at -1, I go to -1. If I'm over here at 2, I'm going to go to 8, and so on and so on and so forth. Now, okay, so I have this nice little arrow diagram. Now, if I'm cubing and I want to go back, I take the cube root, right? And so let's show that these things are inverses of each other. Well, if I take the cube root of x cubed, I wind up with x. And if I take the cube root of y and I cube it, I wind up with y. These are inverses. And it doesn't matter where x is, it doesn't matter where y is. X can be negative, x can be positive, x can be 0, etc., etc., etc. And on the graph, and you're used to seeing this on the graph, because that's how it was presented in pre-calc. These arrow diagrams were not presented in pre-calc, for most of you, if you took it at USF. But let's look at the graph of these things, just to refresh our memory. So here is x cubed, and if I want to graph the inverse, what I do is I switch the x and y axes. In other words, I flip it along the identity line here, and I get that, right? So what I've done is I've just flipped it, right? I've changed x to the y and y to the x, and I get this. Okay. So these graphs are inverses of each other, right? Because they're symmetric along this 45-degree identity line. Okay. So that works well for x cubed. Well, let's consider x squared. X squared is going to be a different little monster. All right? Here, if I have -1, I'm going to map to 1. Now, the question is, where do I go back to? So there's two problems with x squared here. The first, if f of x equals 1, where should I send y back to? Should I send it back to 1, or should I send it back to -1? There are two choices. And remember, for a function, I can't have two choices. Each input needs to go to only one output. So if I've got two inputs coming in, I don't know where to send it back. The other problem I have, if y equals -1, there's no x to go back to. So I'm not using all my y's. So f of x does not have f of x equals x squared doesn't have an inverse. Okay? However, from R to R, and that's important to say. It's important to say that from R to R, I don't have an inverse. But I can fix this. Well, some of it. What happens if I instead restrict f? What happens if I take f and I say, okay, f star, and I'm only going to define it, so I'm restricting the domain to the non-negative numbers. And then I'm restricting the codomain. Instead of letting the codomain be R, or the target be all of R, I'm going to say, okay, I'm only interested in the non-negative numbers. So I'm going to call this restriction, this new function, f star. Now I don't have that problem. Notice now I don't have the problem that I did before. I now, when I go from 1 to 1, there's no negative 1 to go back to, because negative 1 is no longer in the domain. Moreover, there's no negative 1 to get to, because negative 1 is no longer in the target. Okay? So there's no negative 1 to go back to. Moreover, there's no negative numbers, there's no negative 4 to get to. I don't need to worry about those things. So now I can take the inverse, the square root of x, and now I truly have an inverse. Okay? Excuse me. I actually could have solved this problem another way. Now what I've done is I've gotten rid of the positive portion of the domain. Now I'm only dealing with the negatives. Now, this solution, I also have an inverse, right? It's not here. I've cut off the positive numbers from the domain, and now I've sent everything over to the, x squared. I've sent everything to the positives. Well, now I can define an inverse. I just do the negative square root of x, and I'm sending everything back to where I got it. In fact, I could have defined the square root of x. Instead of the convention is to define the square root of x as going from positive to positive. I could have defined the square root of x to go from positive to negative, and it would have been just fine. Okay? The square root of x is chosen. Okay? The fact that I've mapped the square root of x goes from positive to positive is a choice. I could have gone positive to negative. It's a convenient choice, but it is just a choice. And if I look at the graph of these two functions, if I look at x squared here, it's this kind of parabola that we're all familiar with. But we can immediately see the problem, right? Here's that 2 thing again. And then I go ahead and I restrict here. If I try to define a function, I wind up an inverse. I wind up with something that's not a function, right? It's this this thing. I've got two inputs for the same output. Now, if I hold my restrictions to the positives, however, I don't have that problem, right? Because now, when I flip it, I still have a function. Okay. And again, I could have solved this going the other way. Instead of choosing this half of x squared, I could have chosen this half. So choosing that half looks like that, and then when I flip it, I end up with this. So this right here is the flipped version on the negative side if I use this as the input side. So if I use this as the input side, the inverse would look something like this. Now, this property that you're seeing here has a name. Okay, there are 2 of them. So f, if I've got, let's let f be a function. F is onto if for any y there exists an x, so that xy is in f. In other words, f hits all the y's in the target, or every y gets used. Okay, so if we go back to our definition of a function, as you can see, this is analogous, right? Here I had every x gets used. Now, if I want it to be onto, I need to use all the y's as well. And the second condition also has such a conclusion, as such a parallel, and that is I'm 1-to-1 if no y is hit more than once. So if we go back to our x cubed graph, okay, you will see that here I use every x, and I don't use any of the x's more than once. So this function is both 1-to-1 and onto. Okay. Now, compare that to our old graph for x squared. This function right here is neither 1-to-1 nor onto, correct? I can't hit any of the negatives, and I've got 2 numbers here for every positive output. So x squared, defined from R to R, is neither 1 to 1 nor onto. Some other examples. Let's do one of these. The tangent here will hit every x value, right? The tangent function is definitely onto, but it's not 1 to 1. Okay. X squared, as I said, was neither, but if I restrict the domain to 0, infinity, but I still don't leave the target as R, I get a function that's 1 to 1 but not onto. Likewise, if I restrict the target, I'll get something that's onto, but it's not 1 to 1. Only by restricting both the domain and the target for x squared did I get both. Okay. Now, why do we care? Well, because there's this big theorem that actually requires a lot. It's like the theorem, but if you want to prove it, it actually requires something called the axiom of choice. So we're not going to do the proof. But if a function f from x to y has an inverse if and only if f is both 1 to 1 and onto. So you have to have both of these conditions to have an inverse. Okay, so let's look at the calculus of these things. So I'm going to have f and g be inverses, f going from x to y, g going from y to x. Well, that means that g of f of x equals x. So by the chain rule, when I take the derivative with respect to x of g of y, because remember y equals f of x, I get d over dy of g of y times d over dx of y, which means that I get g prime of y times f prime of x. But the derivative of this side here is 1. So that means that g prime of y times f prime of x equals 1. In other words, g prime of y equals 1 over f prime of x. In other words, I can actually think of this as a fraction. The fractional notation makes sense. It's a metaphor, but it's a good metaphor, right? dy over dx equals 1 over dx over dy. Okay? Now, let me show you what I mean by this. Let's look at the differentials. Okay? Let's let y equal x cubed. So what I do is I take the cube root of y equals x. Okay? Well, let's look at this real fast, but note that that's true. Now, if I take the derivative here, if I take the differential right here, I'm going to get dy, because this is 1 dy, equals 3x squared dx. So dy over dx equals 3x squared. Well, but instead of solving for dy over dx, let's say I solve for dx over dy, I get 1 over 3x squared, which is the same as 1 over 3 cube root of y squared when I sub in the cube root of y for the x. That's this thing here is the same thing as 1/3 y to the negative 2/3. So I could have just, if I take the derivative of this straight, of the cube root of y, and I get dx over dy, that's what I'd wind up with by the power rule. Let's look at our example x cubed again. So for x cubed, this will be the x side, this will be the y side. Here I've got f of x equals x cubed, f prime of x equals 3x squared. G of y will equal g to the 1/3. G prime of y by the power rule is going to equal that. So let's look at 1. Well, if on x, f prime of 1 would equal 3 when I sub it into this equation. For y, g prime of 1 equals 1/3. Here, my x side is 2, so f prime of 2 equals 12. Well, g prime of f of 2, or otherwise known as g prime of 8, equals 1 over 2. In other words, I can, when I've got these equations, the slopes are going to be reciprocal of each other. Okay, there's one major caveat. This is a notational thing, and it's evil. And this is one of the biggest warnings I can issue you. Okay? If the notation for this inverse thing stinks, okay? There's kind of a lot of people are starting to use the back arrows, but our book doesn't. Our book sticks with this -1 thing. You do see this instead. So you sometimes see this for notation, but that's not the standard stuff yet. Hopefully that becomes standard, but it's not yet. So if G is the inverse of F, we will say G equals F to the negative 1. F to the negative 1 does not mean 1 over F. It means the inverse. F squared should mean f of x, not f of x times f of x, unless you're a trig function. Okay, so I've seen some people do log squared a couple times, and I've been like, no, don't do that, right? And one of the problems with trig has this nasty stuff in it. Just not nasty in terms of the notation's bad because it's irregular. It's not so much bad. It's just an irregular verb, right? Trig is kind of the oldest thing in math, so it's got notation that, is just for trig in one sense. But so sine negative 1 means the inverse of sine, not 1 over sine. 1 over sine is cosecant. Okay, sine negative 1 is arcsine, and I will try to use this arcsine notation instead of sine negative 1, but your book uses sine negative 1, so watch out. Sine negative 1 does not mean 1 over sine. It means the arcsine. Okay, 1 over sine, the special notation for that is cosecant. Okay, so sine of x to the negative 1. The whole thing to the negative 1 means 1 over that. That's cosine. But the sine negative 1 stuff means arcsine. This notation is confusing. There's nothing I can do. The reason for this notation is because mathematicians hate you. And not you in general class. I mean you in particular watching this right now. Mathematicians hate you, and we're just taking it out on everybody else. Okay. So that's inverses with this big caveat about the notation. Next time, what we're going to talk about is inverse trig. Good luck on your test, and I'll see you next time.